lecture, we learned about the model theory of first-order logic. Today, we're going to learn about the proof theory. So things need to get a little more syntactic. Let me begin with something that you're probably perfectly familiar with. That is the distinction between free and bound variables. But it is so important, it's worth devoting a few minutes to reinforcing these concepts. So when we have quantifiers, like for all x, a, and exists x, a, x is bound within the formula a. So although I have simply written a here, we assume that there are probably occurrences of x within a. Any occurrences of a variable that are not bound are free. So in this thing, it's a little hard to check, but x is a free variable. So y and z are bound. X is free in this formula. Now, an obvious point is that bound variables are local, and your intuitions from programming languages are useful here. So if you think of any scoped programming language where you have local variables, you can rename them without affecting the meaning of your program, provided you don't clash with some name already in use. The same principle applies in logic. So here we are renaming z to z prime, and we have not changed the meaning of the formula. Our proof theory will rely on the ability to substitute terms for variables in formulas. This is defined by recursion in a perfectly obvious way. There are different notations for this. The one we use here, you'll note the variable being replaced is written second, so you could pronounce this a putting t for x, substituting the term t for the variable x. And this may remind you of the notation we saw last time, although it's a slightly different concept where we alter a function that maps variables to values. So that is actually a slightly different thing we looked at last time. Substitution, as I said, is defined by an obvious recursion. So if you have a propositional connective like and, you simply push the connective inside and substitute over the two subformulas recursively. The only tricky case is when you have a variable binding, and there are two separate cases to consider. One, if you are substituting for the actual bound variable. In this case, the substitution has no effect because there are no free occurrences of x in for all xb. The more complicated situation is when the bound variable is different from the one you are substituting for. Now, you want to substitute recursively in the body of the quantified formula, but you also need to be careful that this term x that you are substituting doesn't have any references to y, because any references to y would then be picked up by this for all y here, and that would totally change the meaning of the formula. The last case, if you have an atomic formula, and I have simplified this to a predicate with a single argument, you simply substitute recursively into the argument itself. So I am now remarking again on the slide about how when you substitute, you may not allow a free variable of the term that you are substituting to become bound. And I have an example here, if it's not perfectly clear, that it would be nonsensical. So this formula, for all y, x equals y, is asserting that everything equals x. Now, we don't know what x is, so this is a formula with x as a free variable. Nevertheless, it is a property of x, namely that everything is equal to that x. Now, I have the right to rename y because it's bound, but I clearly should not rename it to x. As you can see, if you do so, we get a new formula here which suddenly contains no free variables at all. And now we have a formula that is trivially true, whereas the previous formula was a non-trivial property of x. As before, we'll need some normal forms, and so we need to have some further equivalences that will allow us to transform first-order formulas and to transform occurrences of quantifiers. The first one is a kind of De Morgan law for all and exists. The second, I guess, is sometimes called the one-point rule, and is simply saying that if you know for all x a, then that's equivalent to for all x a ANDed with any specific instances that you wish. So if t is some particular term, I can AND in a copy of a with that particular term substituted in. And this goes with the idea that for all x a is kind of an infinite conjunction of instances of the formula A. As for the last one, this particular distributive law is kind of easy to understand. So we could, as an example, if everybody is fat and everybody is happy, then everybody is fat and happy, right? That makes sense. This other distributive law does not hold. One way of seeing that is here on the right side. If everyone is either male or female, that does not imply that either everyone is male or everyone is female. As before, we can dualize any of these, replacing for all and exists and an or. And if you take the trouble of writing out the dual versions, it might be a useful exercise, and you can also check the meanings of the two distributive laws for exists, remembering that one of them is not actually valid. Finally, these further quantifier equivalences are specifically for increasing, I should say expanding or contracting the scope of a quantifier. So in every case, we have some quantifier for all x a, and we are, if you like, we want to expand the scope of the quantifier to include some formula b, and we assume we have already arranged that x, which is a bound variable, so we can rename it to anything we like. So x must not be free in b for any of these examples. So b is not really taking part in the quantification. So if you look, for example, in this first example, for all x a and b, b has no occurrences of x in it. So it's kind of obviously true. To see it, you just have to consider b is either true or false. Certainly if it's false, then both sides are false, and if it's true, then the b's simply go away in those conjunctions. The one to be careful of is the last one. If you can't see why the for all turns into an exists, remember that implies has an implicit negation in it. We are eventually going to see an extension of the sequent calculus, but before I go there, there are some things I'd like to mention, some other ways of doing logic. In the second lecture, we saw an example of transforming a formula into conjunctive normal form, a propositional formula, and as we transformed it into conjunctive normal form, it collapsed down to the single symbol true. Because those were equivalence preserving transformations, that was a proof that the original formula was a tautology. This is a very crude way of theorem proving by transformation. Some people, particularly in certain places in the USA, some people have pushed very hard for a strictly transformational approach to proving theorems. The advantage of a transformational approach is it can be clear. You're transforming one thing into another, into true. That looks nice as long as your transformation rules are intelligible. And I have to say, in some of the examples I've seen, that is not actually true. But it must be pointed out that most of these transformational approaches are intended for hand proofs. Our lecture course is not about hand proofs. You will find if you do Gensen proofs by hand, they blow up very quickly, but we are learning them, remember, because of their role in automation. I just want to mention a few things here about how we reason with simplifying formulas by hand. So, if we have P or Q, it is possible to simplify Q under the assumption that P is false. Now, why is that? It's simply by case analysis on P. If P is false, the whole thing is equivalent to Q, and in this case, we are looking at Q when P is false. So if you simplify Q to some Q prime, which holds when P is false, that will be a valid thing to do. Now you say, but what happens if P is true? But if P is true, then the disjunction P or Q will itself simply be true, and Q is not relevant. Dually, for P implies Q, for example, we can simplify Q assuming that P is true. This is perhaps the easiest one to see intuitively. Remember that if P is false, the entire formula will be true vacuously, irrespective of Q. So only when P is true does the value of Q matter at all. So we can simplify Q under the assumption that P is true. Now we can do some simple quantifier reasoning by hand using such techniques as these. So let's start with this formula here. That is, there is some x such that x equals a and p of x. Now you, probably looking at this, have already realized this must be equivalent to p of a. But if we want to prove it formally, we need to go through at least some kind of logical reasoning. So our first step is what I said on the previous slide. That is, in this case it's conjunction. If I have a formula of the form of a conjunction, in this case x equals a and p of x, then the value of p of x only matters if x equals a, because if x is not equal to a, the entire thing will be false. So I assume x equals a, and I replace x by a here. Now I can use one of the equivalences I showed you to, in this case, contract the scope of quantification, because p of a no longer refers to the bound variable, and I can therefore pull it out of the quantification. And as a general rule, minimizing the scope of a quantifier will make your life easier. Finally, we note that exists x equals a is trivially true, and so it collapses down to p of a. Well, whatever. The next example may be more interesting. The nice thing about this formula is it looks totally implausible. It says that for some z, if p of z, then p of a and p of b. So this formula looks, well, false. And in fact, in constructive logic, it does not hold. It is not valid. But we're in classical logic, and it turns out this thing is easy to prove. So first of all, we note that to the right of the implies symbol, the bound variable isn't used at all. So we can use one of those transformations we saw already to contract the scope of the quantifier, which, as I mentioned, turns from exists into for all. And so we are left with this thing, that is, for all z p of z implies pa and pb. And that's obviously true, right? I have p of z for all values, possible values of z, so in particular p of a and p of b. I can, to really belabor the point, I can use this so-called one-point rule a couple of times to expand out and put out explicit copies of the body, and then it definitely simplifies to true. So here we have seen that this very unintuitive looking formula that we started with can be transformed into true in just a couple of steps. And this perhaps is an argument that reasoning by transformations does have its advantages. Now, I would like to make a small digression. Principia Mathematica was a very important 3-volume work written by Whitehead and Russell in 2010, I think, to 2013. This book introduced a rather crude proof system, which we will look at in part so that you will feel better about having to learn more sequent calculus rules. The book as a whole was trying to show that mathematics could be reduced to logic. It did this by developing certain topics in mathematics, simple theorems about sets, logic itself, arithmetic, and trying to get to more and more advanced mathematical topics, all in a very, very low-level way with strictly logical proofs. There also, in the beginning, there are a lot of logical paradoxes explained and analyzed, and that's actually interesting to read. Turns out it is still in print. Now, the funny thing is, when they wanted to publish it, Cambridge University Press said, we don't expect this to be a big seller. It will lose, we think, about £600, which back in 1910, you can say that was worth more like £60,000 in today's money. So the authors had to come up with £10,000, again in today's money, to get their own book published. The Royal Society providing a further £20,000, and then CUP being willing to stand the loss of a further £30,000. Luckily for everybody, it turned out to be more successful. I think it was a slow seller at first, however. And the paperback edition is still in print, actually worth buying. And here's what it looks like. I used to tell my students to take a copy of the book into the college bar and show it to their friends. Unfortunately, all the college bars are closed, but I suppose you can still take a screenshot of this and show your friends, and this is what I am studying in the computer lab. What's going on here? Well, I am not going to go into great detail. He has this weird notation with lots of dots because he didn't like parentheses for reasons I will never understand. So the dots somehow replace parentheses. Everything is done with a lot of very low-level rules. Finally, I'd like you to notice that this is page 362, and the result proved here is 1 + 1 = 2. Now I would like to show you a nicer way of proving theorems, and I hope you are in the mood for it now. So we take our existing sequent calculus for propositional logic, and we will need to add 4 further rules to it. 2 for the universal quantifier and then a bit later 2 more for the existential quantifier. Now, what is going on with these rules? The one for all on the left is perhaps easiest to understand. Here we're in a situation where we're trying to prove something, some delta, which you may remember is a set of goals to prove. On the left, what we are allowed to assume in this case is various formulas in gamma, but also something of the form for all xa. And this rule says you are allowed to substitute any term t for this for all xa, for this quantified variable, and it suffices then if you can prove what you're trying to prove with the help of this instance of a. Although I haven't copied the quantified formula to the top here, in general you can. So if you have for all xa, you can keep it as you apply this rule, and possibly to use it again later at some point in the future. And indeed, if you know for all xa, in general you will need to use that more than once in order to prove your result. On the right, we have a different rule. This is to show for all xa. It simply says show a. This may seem a little odd at first, but in fact it's how mathematics work in general. So if you want to show that, I don't know, all farmers are furry, you say let f be a farmer, and then for some fixed f, and then show that f is furry, and that is how you show all farmers are furry. So you see here we have x, a variable with a very important side condition that x must be a fresh variable. Now it's written here as not free in the conclusion, which basically means x is not mentioned in gamma and not mentioned in delta. So x is absolutely fresh, used nowhere else, and in that case you can simply drop the quantifier, and if you can prove this for this arbitrary x, then you have proved it for all x. And just to reinforce why we have this proviso, this side condition, look otherwise at the following proof that would be allowed. So at the bottom here, or let me look at it from the top actually. So clearly, py sequent arrow py, that's a basic sequent, and it is triviality because it is the same formula. But if we forgot about this side condition on for all on the right, then we would allow this inference. And this inference doesn't make any sense at all, because this is basically saying if p holds for some y, one particular y perhaps, then it would hold for every y. That is nonsensical. And that is just an example of why we have this side condition on the for all on the right rule. Now for a very, very simple example. Now here is where, if we were in a live lecture hall, I would be doing the proof on the other projector. As I can't do that, we just have to walk through it. First, look at the bottom formula. Very often the things that you are asked to prove will make some kind of logical sense, and if you can see any sense in them, it's worth spending a moment convincing yourself that the formula is true. Although I have to admit some of the examples are pretty complicated looking. But here though it's easy. On the left we have for all x p of x, so p is always true. On the right for all y p of f of y, and this says p is true for everything of the form f of something. And it's pretty likely that this will be a theorem. How do we go about proving it? Now here is a very important tip when you have a for all on the left, you may be tempted to use the for all on the left rule to put some term in here. But you need to know what that term should be. And we don't know yet because there are no free variables in this sequent. So do for all on the y instead. That is the only other symbol we've got. And remember, with the for all on the right rule, we're allowed to strip off the quantifier. There are no occurrences of y anywhere else. So we strip off the quantifier. Now when we do for all on the left, we know exactly what term to plug in, namely f of y, and bingo, we are done. The next one, oh dear, what a mess. We start with the sequent on the bottom. This looks like a theorem to do with restricting the scope of a quantifier. So here on the left, we have a quantification with x over an implication, and on the right, we have a different formula with a quantifier further inside. So we're trying to prove that sequent is valid. What can we do here? Remembering that sequent rules only apply to the outermost symbols, we see a for all on the left side and it implies on the right side. As I told you before, you shouldn't do a for all on the left unless you know what term you're going to put in for x, and we don't. So we say, oh well, can always do this implies on the right instead. So we do that, so you see p goes over there, the implication goes away, and we've got for all yq of y. Again, we don't do for all on the left because we still don't know what term to put in. So instead we do for all on the right, we strip away this quantifier, and now we are here. We are trying to show q of y, and now we have a very good idea what to replace x by when we do for all on the left. That is, x should be y. We plug it in, and the rest is just propositional reasoning, and we're done. And here are the existential rules. I suppose it's easiest to look at exists on the right. This says, if you're trying to show that there exists some x such that a is true, just exhibit it, right? If a holds for some term t, then obviously a holds for exists x. Then obviously we have exists x a. This turns out to be the exact dual of for all on the left. As for this one, here is where we know that something exists. There definitely exists an x such that a, we're allowed to assume it. So what do? We can reduce this to a thing where the thing that satisfies a is simply called x. In other words, we strip away the quantifier and we're saying, yeah, you say that there exists x such that a, well then, give me such an x. And we still call it x. And it's subject again to the condition of being fresh. So x must not be free in gamma or in delta. So it's entirely a fresh variable, and a satisfies x. Now there's one thing a little odd about this rule. So in particular, exists on the right, as I mentioned, is exactly dual to for all on the left. And in particular, you're allowed to keep this quantifier, and so that you can use the rule again later. That would only happen if you did such a thing. You would then have multiple formulas on the right-hand side, which we don't often do, but is necessary in general. Such proofs tend to be quite tricky and are the sort of things you would find in a particularly annoying exam question or exercise. So this formula here, the one that we did easily using transformations, is not so easy to do using sequent calculus rules. You can try it as an exercise. Here is a more straightforward proof, though a big one. So first of all, as an example of this distributive law here, I suppose we could say if either somebody is drunk or somebody is lazy, then we know that somebody is either drunk or lazy. So that is likely to be true. Of course, we have to prove it, and how do we go about proving it? Our usual sequent calculus business. We eye up the sequent and we see we've got an or there as the outside connective on the left, exists as the outside connective on the right. Now, just as with for all on the left, you shouldn't do it until you know what term to plug in. In this case, we have no idea what term to plug in for exists on the right, so we don't bother with it. Instead, doing this disjunction on the left, which is something we can always safely do. So we say we do this disjunction on the left and we get two sequents here, very similar looking. This has exists x p of x, that has exists x q of x. And excuse me for omitting all this material that there wasn't room for, but this is almost exactly the same proof that I have hidden. Now looking over here, again, we do not know what term to plug in for exists y, so we leave it there and instead do exists on the left. X is not free anywhere in the sequent, so we can strip off the quantifier and we have p of x. Now we know that x is the term to substitute for the quantifier on the right, and the rest is trivial. As for this example, and this is just slightly different, but it's quite important to see how it is different. So the sequent there is saying if there exists exists x px and exists x qx implies exists x px and qz. One can see, for example, that if there is someone who's male and there is someone who is female, that does not imply that there is someone who is both male and female. So we expect this proof to fail. I can remark, on exams I frequently see students causing such proofs to be successful by cheating. This is, however, worse than not proving the theorem at all. So let's start and try to do this. Now this proof should fail, and a typical exam question will say to either prove or give a counterexample. So here it is enough to give a counterexample such as the one I gave already, except a little more precise than just talking about males and females. So you have to go to a little trouble to try and make some kind of an interpretation that falsifies this sequent at the bottom. But I'm going to attempt to prove anyway, not because it has any value in general, but so that you will see how our logic mechanisms prevent this invalid sequent from being proved. So we go through our business, we see the and on the left and we split it up, always a safe move. We have two existential quantifiers, excuse me, on the left, and we arbitrarily eliminate the first one, p of x. And now here is where we have a problem. The side condition exists on the left rule prevents us from simply dropping the existential quantifier in front of q. We have to rename the variable first. Let's say to y. And now, of course, you can see when we want to take off this existential quantifier on the right side, we could put in x, we could put in y, we could even try and keep it and try to do both, but none of this will help us, because this is an example where, to use our male-female example, x is the male, q is the female, and there's nobody who is both, and therefore this cannot be proved.